Hello everyone, I am Ahmad Alsaab. I'm working as a system modeling engineer in ESI. I have a PhD degree in mobile robotics from Newcastle University. Currently I'm living in Wolverhampton in UK. So today I'm going to give a presentation about our paper, parameter estimation methods for fault diagnosis using Modelica and FMI. My presentation includes 4 points. The first one, introduction, will give some basic theory about the methods used in condition monitoring system. We will talk also about the local estimator to estimate the parameters using Modelica. Then the global estimator, which is implemented outside Modelica to estimate the parameter using FMI. And finally, we will conclude what we saw in this presentation. Introduction. So there are three categories for the condition monitoring system. The first one use just data, and some people call it black box. And this kind of method maps between the input and the output, and without considering the mathematical equation of the system. This method is good, but if you have historical data. The second category is the model-based method, the white box, which use the mathematical equation to define if there is fault in the system or not. The combination between the both system called the hybrid model or the gray box. So we have here a diagram about estimating or defining faults using model based methods. So we can see here we have state estimator. The state estimator has the same input of the physical system. The state estimator will produce output, estimated output. The estimated output will compare it with the sensor data coming from the physical system. The error between the estimated outputs and sensor data will be fed to the estimator to adjust the parameter of the system. Then at the end of the estimation procedure, there will be an estimated parameters. Actually, before we started the estimation, we know the parameters for the healthy condition, and we have the estimated parameter, so we can compare between the estimated parameters and parameters for the healthy system. From that, we can define the location of the faults and the amount of the faults. In our paper, we classify the estimators in two categories, local and global estimators, and we will see the difference between them in the coming slides. So for the local estimator, is implemented using Modelica language, and it's used to estimate the parameter of one component. You can see here we have actual model, and we have model with the estimator. So the aim of the estimator to estimate the parameters of the second element. So in this case, we kept all the model, and we replaced just the equation of the element 2 with the estimator algorithm, here. And this is the reason why we said local. We just use a part of the system, not all the system. The local estimator was implemented using three different methods. We call it the direct method, regressive least squares, and particle filter. To test those algorithms, we choose a simple mechanical model uh, with two springs and two masses. What we change the mass, the value of the mass 1 from 5 kilo to 2 kilo at the time t equal 5 seconds. And we take the displacement of the second mass as output of the system or as a measurement. So, and you can see here from the displacement of the second mass that the pattern of the oscillation is changed after t equal 5. We started with the direct method, and the direct method works just by modifying the target parameters to make it unknowns. Now, if we make the target parameters unknowns, that means we'll increase the number of unknowns, and in Modelica, the number of unknowns should be equal to the number of equations. So to avoid that, what we can do, actually, we can change the parameter. Like here, we need to estimate the M1, so we change it from parameter to variable. So we have, in this case, unknown, and we can see here we have displacement as unknown, but because we record the data, we can make it input, and in this case will be known. So we kept the same number of unknown with this, and the same number of equation. So for this one, for this method, as we say that we need for each target parameter a reference signal. And in this case, if we have a lot of target parameters, we need a lot of measurements. Usually this system is very simple to implement. As we saw here, we just changed the definition. We didn't do anything, just changing the definition. But this estimator is very sensitive to noise. One is the regressive least square estimation, and this algorithm is well known. If we have a linear system, we can estimate the parameter here, which is the coefficient alpha 1 to alpha n, and we have x1 to xn is state. So we can estimate those coefficient of parameter if we have enough sensor data. So we can see here, after the implementation of the least square method, the estimator managed to estimate the change in the value of M1. What about this method? This method is easy to implement, robust against sensor noise, but the main disadvantage of it that it's only used for linear systems. The third one is particle filter system method. The particle filter use 4 stages to tune the parameters, and this system can be used for linear system and non-linear systems. So we can hear, although we have a lot of ripples in the output, so we can see that the system, the estimator managed to define the right value of the mass. The main drawback of this method that it's time consuming, especially for large methods, and that can limit this method if we have for online applications. Now we will move to the second category here, the global estimator. The global estimator is implemented outside Modelica. For our paper, we used Python to implement the global estimator, and the global estimator use the whole model, not just part of it like the local one. So we call it global because all the model will be used with this kind of estimator. The block diagram here explained explained the global estimator. So what we have here, we have the estimator algorithm. The input of the estimator algorithm is the sensor data and the outputs from the model, which was converted to FMU. So the model here, the estimator uses the model as a black box without need to know exactly what inside the model as a mathematical equation. So the FMU file, as you know, we can use it in with Python. So the output of the global estimator is parameters. So the estimator tune the parameters to make the error or the difference between the sensor data and the outputs very small. We choose particle filter to implement the global estimator, and particle filter can use the model as a black box. No need to know the mathematical equation for the model. So what we have here, an example, we have a thermal model, and we have data from a wind turbine component, and there was actually a fault in the thermal data. So if we look to our model here, we have 4 parameters. We have friction, we have heating capacity, we have thermal resistance, and we have the cooling system temperature. And you can see here there is a difference a gap between the estimated output in the blue line and the measurement in the red line. So the estimator work with the FMU file to tune the parameters to close the gap, as we can see here in the output of the estimator. And when we checked the output of the estimator, we find that okay, the friction changed from 0.7 to 0.93, and we can define okay, there is a problem with the friction, and we can know the amount of the friction here. So also we need to prove that our method is suitable for multiply sensor and faults. So we have an example here, hydraulic system with 3 sensors. We have 2 pressure sensor and one displacement sensor, and 2 faults. Addition losses 1 and addition losses 2, and those faults controlled by a parameter inside them called intensity. So we change the intensity for fault to 0.2, and by changing that we can see for the healthy condition and the faulty condition, there is an error between them, a gap between them. So from that we can know that there is a fault. Now we apply the global estimator to define amount of the leakage or the intensity of the fault. By applying the global estimator or particle filter, we find okay, particle filter managed to close the gap between the measurement and the simulation, and make it, you can see here it's about 80 bar, and the estimator managed to make it less than 1 bar. After that we check the parameters. We find okay, the right parameter is 0.2, and for both value for addition losses 1 and addition losses 2, and we can find okay, the system managed to grab the fault. So this approves that our model can be used for many faults. The final conclusion, so we we introduced and we examined two different types of estimation methodology, local and global estimator. Also, we use different different methods to implement those two kind of estimators. We used the direct method, particle filter, and least square method. We used systematic representation of the fault using SRR library to produce leakages in the hydraulic system. Finally, we we used the estimator to define a fault in real system, in the wind turbine system, and the estimator was able to find the amount and the location of the fault. Thank you very much for your listening. Please, if you have any question, feel free to ask.